Years as a NASA astronaut, flew on SDS-114, which was the return to flight mission after the Columbia disaster, spent over 13 days in space, and has served as the head of engineering at the Johnson Space Center. He served as an adjunct professor at several universities and is founder of an educational not-for-profit organization called the Epic Education Foundation. Now, his book, Mission Out of Control, comes from all of his experience at NASA. I think what you'll find is this will be an entertaining discussion of all the things that go on at NASA. So a little bit of behind the scenes and no holds barred is what I would call it. But Charlie's been, as I said, a great friend of the museum over a number of years. He's in our Hall of Fame up on the second floor. And I'm not going to waste any more time. Please welcome NASA astronaut Charlie Camarda. Oh, by the way, he's from Queens.
Queens, not Long Island. And I want to say, I feel like I'm a friend of the Cradle of Aviation. I love these people, and I want to thank Andy, Josh, and Carol for inviting me to do this and to come out here and to talk to you about this book. I really appreciate the opportunity. This is the first day the book is on sale. This is my publication day. It's my first book signing. I've not written any other books. And it's not your typical astronaut book. You know, it's not a memoir. I do have some great stories in it. But my career is different than a lot of NASA astronauts. So, as you can tell from the title of the book, Mission Out of Control, it's not your typical story. I worked for NASA for over 45 years. I am the oldest rookie astronaut to fly in space. NASA astronaut, I was 53 years old. Probably of all the astronauts, I worked for NASA the longest. So I started out as a research engineer for 22 years at NASA Langley in Hampton, Virginia. Right out of college at Brooklyn Polytech. I left my little Brooklyn Polytechnic School of Engineering, graduate there. I left my little Italian mother crying her eyes out in Ozone Park, and I drove down to Virginia, and it was an amazing cultural change for me. That was my first experience with really different cultures, the Southern culture. And I had an amazing 22-year career as a researcher with some of the most amazing people I could ever meet. Some of the tops in their field in all the different disciplines of engineering, aerospace engineering, structural mechanics, heat transfer, aerothermodynamics, fluid flow. These people were amazing. These people had written books. These people were tops in the world. And during my internship, between my junior and senior year in college at Brooklyn Poly, one of the professors says, you know, Charlie, there's an opportunity to basically do an internship. Well, he said it to the whole class, there's an opportunity to do an internship at NASA Langley. And 3 kids' hands raised up, and me and Pete Naffo went to NASA Langley. Sammy Ayala went to Marshall Space Flight Center. And meeting these amazing people and working with them, I said, wow, I was touching genius. You know, these people were just amazing, and they actually spent time talking to me and mentoring me. And in that short 2-month span of time, I realized this is what I want to do with the rest of my life. And so, you know, when I talk to students and when I talk to parents, I say, you know, if you have kids and they don't know what they want to do, let them do internships. Let them work all over. And let them see what it's like, because I was really lucky. And so that changed my life completely. I was lucky enough to get the job at NASA Langley Research Center, and right out of college I drove. I went down the Eastern Shore, and when I went to get gas, the gentleman changed my oil, or he checked my oil, filled my gas tank, and then I went to give him a tip, and he said, oh, no, we don't take tips. And then I thought, wow, where the hell am I driving to? And what a difference in cultures was I going to experience. But it was amazing life, and I loved doing it. I loved being a researcher. But then something happened. NASA wasn't doing applied research anymore. You know, we were not spending enough money in doing applied research. They were cutting back funds, and I was really not happy with the direction NASA was going, the way they were promoting certain people that weren't the best of the best, the technical people at these high positions. And so that's when I decided to be an astronaut. And when I became an astronaut, and when I decided to apply to be an astronaut, it wasn't because I wanted to fly in space. It was because I had a young daughter, and I just had gotten custody, and I said, you know what? I want my girl to be raised and not be afraid of anything. And so, wouldn't it be cool to travel with me in this and have this experience? And because her father's afraid of heights, can't swim, and is claustrophobic. So if she was going to learn how to overcome her fears, this was a good way to do it. And she went through that journey with me, trying to survive in water survival, and what that was like. And that was actually the scariest moment in my life, was trying to pass water survival as an astronaut. It wasn't being strapped into the space shuttle. I was in more fear of my life, was totally calm, practically asleep when we launched into space. But what I noticed when I was training as an astronaut was what a difference the culture was at Johnson Space Center. Okay? I grew up with these amazing research people. And now I was sitting in an office with other engineers around me, and also test pilots at Monday morning meetings in the astronaut office. And I was amazed that these pilots weren't paying attention to the details that were being presented on the different anomalies we were seeing on the space shuttle. And I was amazed by this. I'm looking at this, and I'm kind of experienced in thermal protection systems and heat transfer and high temperature structures. And I'm saying, wow, these guys aren't paying attention to this, and people were giving presentations as a young astronaut, and I saw on the wing leading edges some of the things that I just spent a lot of time designing as a researcher. The wing leading edge on the space shuttle is made out of a unique material called reinforced carbon-carbon. Okay, it's a composite material with carbon fibers and carbon matrix, right? And the only thing preventing that wing leading edge from burning out during the extreme heat during Earth entry for 15 minutes, it experiences over 3,000 degrees Fahrenheit. The only thing preventing it from burning up like a piece of charcoal is a thin coating, 40 thousandths of an inch thick, of silicon carbide material, one of the most hardest, most brittle materials out there. And if you lost a thumbnail-sized piece of that material, as that entire vehicle is coming into the atmosphere, you burn up. Okay? And I'm watching these experts, supposed experts, show me pictures of little chips of coating coming off at the highest heated regions of the wing, and the shuttle survived. And after they presented that, I went up to this man, Don Curry, an expert in this material system. I said, I have really good friends of Charlie that are experts in my branch that I had at Langley. This is a thermal stress problem, and I think they could help tell you what you're seeing, this small anomaly, what's causing that, the root cause, so that we can prevent a tragedy. And they said, don't worry about it, we got this, Charlie. And I didn't think twice about it, right? And then all of a sudden, this happened. The space shuttle, Columbia happened. I was training in Russia. I had to train for about 9 months. I was picked to be a backup crew for the International Space Station. One of the, this is when we first started sending crews up there for 6 months on the International Space Station. And a cosmonaut came across the common area at the Yuri Gagarin Cosmonaut Training Center in Russia and told us that we lost Columbia, SDS-107. And these were 7 of my friends, 3 of them classmates. And we went into the cottages. It was a freezing cold day. And we went into the cottages in Russia, in Star City, Russia. And the American crew were huddled around the TV. And we were watching, well, this was me training in Russia, which was, they had a pretty tough educational system there. It wasn't really great, and if you could tell by my face, you could tell how bad it was, right? But I was training in Russia, and this is what we saw. You know, and I was looking at this, and we were deeply saddened, we were in shock. But when I saw this, I was totally angry. I was pissed off. I was angry. I was furious. I was mad. How could really good engineers at Johnson Space Flight Center not know that this was a problem? Right? I studied wing leading edges and not impact, but structural mechanics, thermal structures. The largest piece of foam, over 2 pounds, right? About the density of styrofoam. It's like a 2-pound solid styrofoam cooler traveling 545 miles an hour, slams into that wing with a very brittle, thin coating, and no one could think that that would be a problem. And they told the crew on orbit, don't worry about it, it's not a problem. Matter of fact, they weren't even going to call the crew. The only reason why they called the crew was because they knew they had a media event and the media knew about this and they would learn about it. Okay, so they told the crew, yeah, you got hit with a piece of foam, don't worry about it. I was totally pissed. And they wouldn't let me go back to Houston for another week because they wanted us to keep training. I knew there was no reason for us to keep training. I knew we weren't going to fly for about 2.5 years. So when I went back to Houston, you know, and this is, you know, they made that bad decision, and everyone remembers it breaking up across the sky and picking up 85,000 pieces of material, putting it all together, and then realizing that, you know what, it probably hit the wing leading edge, right about the worst possible location, right about in this region, and that's what caused the tragedy. Right? That's what caused the problem. And when you look at that wing leading edge, what happens is you get a crack, the crack grows, you get a hole, hot air comes in, very, very high energy, very, very high heating, and it basically vaporized the metallic structure of the wing. And so what you see there in that silver lining inside the wing leading edge is really a vapor deposited superalloy material. That's how hot it was. And we lost the vehicle. And what I learned was, and so what I did was, immediately we had to understand what caused the problem. And what we learned was that, yeah, we could understand the technical cause of the problem, but we learned from this accident that the real cause of the problem was the culture at NASA, right? And so as a researcher, I knew nothing about culture. For the next 15 years, I mean, I did a lot of things. I also flew in space during this time, but I had to dive in and understand what is this thing called culture and how does it happen and how does it allow people to make these really bad decisions, right? And we're seeing this happen right now, not only at NASA, but also at companies like Boeing. Right, 737 MAX, and all of a sudden they're bringing up culture is the reason for these tragedies, right? And so immediately I told my boss, you know what, I don't need to fly in space. I could take a hiatus. I know lots of people for 22 years all around this country working in hypersonics. I want to form these teams and solve these problems. And my boss said, no, Charlie, you could stay as an astronaut. And train, yada, 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 and I'll let you form these teams. He was a really good guy. Kent Rominger, one of the best heads of the office we ever had. He's right now at Thiokol, ATK Thiokol. But what I learned was that, you know, why did these NASA engineers make such a sophomoric mistake. A sophomore in high school, college, would have been able to tell that the analysis they were using was totally inadequate. People were afraid to question the people that were telling them the foam wasn't a problem. They weren't allowed to question them. And so the first half of that book goes through in excruciating detail what is culture? What are the different attributes and different types of cultural dysfunction that these great people around the country identified, which caused accidents like Challenger and Columbia? And so I go through that and I explain that. But one thing that they missed, I think, that I was able to see that they didn't see, and it was because of my background as a researcher, was that these great sociologists and behavioral scientists, when they analyzed the cause of the accident, they really didn't understand the difference between an engineer, a technical person, and a researcher. We have a professor here from NYU, the Tandon School of Engineering. They know the difference between a researcher, and they do research, and they train students to get their PhDs, and how do you conduct research? And that's what my mentors at Langley taught me. And so the real reason for these accidents was the loss of that research culture. And so in the first half of the book, I talk about how did NASA lose its way, which is very similar to how Boeing lost its way, right? You hear a lot about when they're not concentrating on technical anymore, and they were more worried about production culture and schedule and budget, yada, yada, yada. And that's true. But what happens is when you see these little anomalies, these little flakes, chips of coating come off, a researcher would look at that and they would not be satisfied until they understood exactly what caused that problem. They go in the laboratory, try to recreate that the environment and create that anomaly in the laboratory, but more importantly, they develop the analytical techniques to be able to predict how something's going to fail. That's how I was taught to be a researcher, right? And amazing, I listened to a Joe Rogan podcast, and he was talking to Logan Paul, of all people, and somehow they started talking about research. Joe Rogan knows more about research than 90% of the people that I know at NASA right now. And the way he described his understanding of research. And by the way, it sounds like I'm going to be trashing NASA a lot, and I am. But I love NASA. That's why I didn't leave. So, I saw that our own engineers weren't able to do this. We were missing that. And I describe in the first half of the book, how did we have this gradual slide from an amazing organization, pre-Apollo, to what we have right now? How did we have these two tragedies? How were we not able to fix the organization? I describe how that happened from the NACA days, the National Advisory Council for Aeronautics, when we only had research centers. And the reason for having those research centers was because the United States had no aircraft flying in World War I, even though we had the Wright brothers. We were surpassed by the Germans, the French, and the British, and we had to be the best country in the world in aeronautics. They developed NACA in order to understand everything about the theory of flight and how can we use that applied research to make our industry the tops in the world. And that's what we did. World War II happened, and because of the NACA, we did phenomenal in World War II. So then comes Sputnik, then comes Apollo, and what happened was all of a sudden NASA grew tremendously. We had to start farming stuff out. We had great engineers from the Germans, Werner von Braun and Marshall Space Flight Center. We had NASA Langley, and we actually took that DNA from those NASA centers and started the other space centers like Kennedy Space Center and Johnson Space Center. So it literally was that transfer of DNA. But how we did business when we were research centers changed drastically when we became this large bureaucratic system. Okay, and that's very similar to what happens in these other large organizations like Boeing, whether it's in the nuclear industry, the medical industry, you name it, right? And so you don't have one uniform culture. You have a confederation of cultures and subcultures, right? And all the way down to an individual team. Your teams can have unique cultures. And so the teams that were working on the shuttle O-ring problem or the impact analysis assessment for Columbia and one for Challenger, one of those teams becomes dysfunctional and they don't make the right decisions. They don't have the right expertise within their team to make the right decision. They're not psychologically safe. They're afraid of saying what they don't know. They become arrogant and they make bogus decisions. They make really bad mistakes and accidents happen. So how do we solve this problem? Because all of these systems are complex. Complex systems, you have hundreds, thousands of different disciplines, different components that interact and interface. And so it becomes very difficult to determine a priori what's going to happen, what's going to fail, right? In fact, these problems are also highly coupled, right? And they're nonlinear. So very small changes in parameters can have exponentially different results. And so tragedies can happen very quickly if you don't understand it. And so how do you solve these problems? And so what I did was I looked at all these different accidents that we have, whether it's Columbia or wherever you see, the hardware is speaking to you. It's telling you there's a problem. You see a little something not right. Something is wrong. On Space Shuttle, it was large pieces of foam coming off and striking the orbiter. Diane Vaughan calls it normalization of deviance. It wasn't designed to do that, but when bad things happen like that, it's deviant behavior, but you know what? But we landed. Damaged the hell out of the shuttle tiles, but we landed successfully, and it's normalization of deviance. We get used to seeing anomalous behavior, and we tend to make ourselves believe that we understand what's really happening, even though we can't predict it, but we lull ourselves into believing that we are getting a greater and greater understanding of the problem, and we don't, and we become more arrogant, and we think we're the only ones that we can handle it, and we don't need to call on anyone else. We don't need to call out to those geeks at Langley that are playing in the sandbox. And so there's discrepancy. You know, the people that have the knowledge, that are the experts, are looked down upon, you know, and it becomes very difficult for them to raise their hand. And so it's very complex to understand this human behavior and what causes this culture, right? And so I could see it because I was raised as a research culture. I could see all the things wrong. But after the accident, I started studying it. And so when it came time to actually put these teams together, right, to actually figure out what caused the problem, right, I want to jump around because I don't want to bore you with all these slides like I did all those other people. When it came time to actually solve this problem, you know, and they said, well, Charlie, how do we solve this impact problem, right? Is it not working now? Did I just lose it forever? Somehow?
You didn't solve the problem.
Okay, wait a minute. So, it's taken a long time. This thing takes a long time, I guess, to reboot itself, maybe. I don't know. So, all right, that's why we have IT guys, folks. But, so they were struggling to figure out, how do we predict when this large piece of foam hits a vehicle, what happens, what kind of damage we're going to have? And I said, you know what, I'm not the expert, but I know the right people at NASA Langley Research Center, at Glenn Research Center, and I know we could put the right teams together to do this. And they said, "No, it's okay. We don't need your help. You don't have to do this." I don't know why I did that. I'm sorry. But I did it anyway, right? I did it anyway. And because I have the Friends of Charlie network, thank you. Because I have the Friends of Charlie network, the center directors, I just called them up and they said, "Hey, I need Ed Fasanella at NASA Langley. I need Matt Mellis at Glenn." And I know because they spent over 30 years doing research in impact dynamics, crash dynamics of small airplanes, of helicopters. These guys have worked and honed their skills for over 30 years. You would never hear them call themselves an expert, right? Put together these teams of people, right? And this was a problem. We were losing large pieces of foam since the first shuttle flight. No one had the imagination to say, what if that large piece of foam hits the orbiter that has the crew in it? What would happen, right? For 30 years, they couldn't solve this problem. These folks, we used a research approach to solving this, a building block approach. And what these people do is they go in the laboratory, they test small pieces of foam impacting a load cell, and they evaluate it and compare it to their analysis. And they understand, were we able to predict this? How did we predict this? Did our failure theories work? So that we can understand how this foam is going to behave when it strikes something at a high speed. Then they go and they look at the material, the carbon-carbon material that the wing leading edge is made out of. Small tests, could do hundreds of them very rapidly, quickly, and they analyze how this material is going to behave at various speeds, at various energies, until you fail. Because we have to test the failure to prove that we understand how this is going to behave and what's going to happen. And when they did that, then they looked at, now we could take that analysis, since we verified it, we've correlated it with hundreds of tests in the laboratory very quickly, we could build up and replicate and simulate a full-scale wing leading edge, and we could predict how it's going to fail. And so they modeled the impact of the Columbia foam, and then they ran a test, and NASA was going to run this test without doing the analysis until I told them to stop. Then they ran the test at Southwest Research Institute in San Antonio, simulating the exact same conditions as the crew on orbit, 545 miles an hour. They blew a gigantic pizza box size hole in the wing leading edge. And those people on the ground didn't think that there was going to be any damage. People at Johnson Space Flight Center, when the crew was in orbit, the crew could have had a huge hole in the wing leading edge. And they had people at NASA that could have solved that problem in 3 months' time. They would have had the answer that they needed, because foam was coming off. They only did it in 3 months' time. Foam was coming off. When the accident investigation looked at it, there was over 45 instances where large pieces of foam came off. There was a piece of foam that came off, months before the Columbia accident. A large piece came off in the same exact area, hit the skirt of the solid rocket motor, dented a piece of metal, and they kept flying the vehicle. Okay? This is what made me so angry, right? So I was able, and in the book, in the second half of the book, I talk about really, how do you create these teams? Because I'm not a genius, but I learned by being a researcher. How do you create teams? How do you create high-performing teams? How do you organize them and teach them how to conduct the analysis to solve these anomalies, the root causes of these anomalies, very quickly? Because that's the best we could do. Because when we're testing these very complex systems, we can't predict failure, but the hardware tells us something. We will see something, just like I saw chips of coating coming off the wing leading edge. If they would have allowed me to put my team together, we would have solved that problem. I was fired from my job after I flew as director of engineering because I stood up and said, we're not safe to fly. there were several other pieces of foam on the vehicle we should have taken off. On my vehicle, before we flew, we said you should take off this protuberance airload ramp. It's a large piece of foam going down the cable tray on the side of the external tank. And the folks told us, you know what, you don't have to worry about that, because there's only a 1 in 10,000 chance that that's going to come off. And you know what happened? You know what happened? I'll show you what happened. I got to go back. I'm going to go back because I'm not going to touch that thing. I'm not going to touch that thing. They told us, you know what, we don't have to take that. Oh, I don't have it. I don't have it. Uh-oh. Okay, I don't have it. I don't have the video. Anyway. When we flew, a large piece of foam came off the vehicle and almost hit our wing leading edge. So when you go to watch the, Eileen Collins just had a movie. My commander made a movie, and it's, okay, here it is. So, first near miss, return to flight. We get selected to fly. Somehow I'm allowed to fly in space, even though I was raising hell the whole time during this return to flight tragedy, right? And people said, you know, you have a 1 in 10,000 chance the foam is going to come off. And this is my vehicle launching, right? This is the belly of the vehicle. There's 30,000 shuttle tiles up here. This is the external tank down here, this orange thing. This is the solid rocket motor. There was a large piece of foam called the power ramp, and they said, you know what, you don't have to worry about that power ramp because there's only 1 in 10,000 chance. But they really didn't know what was causing the foam to come off, right? And these people use some predictive techniques, and let me tell you something, probabilistic risk assessment is garbage unless you've done enough tests and you understand where the errors are. And these people misuse that system. After 2 minutes, solid rocket motors are jettisoned, large piece of foam came off. Eileen Collins' movie Space Woman, they just premiered it. It comes out. People on the ground didn't know this happened, right? That large piece of foam, 1 in 10,000 chance, the probability went from 1 in 10,000 to 1 in 26, right? Yeah, tell me about it. I flew in space, then I became director of engineering, and I had to change the culture in engineering. And I had to make sure these folks were going to do it right, and that was a tough job. And as director of engineering, I stood up on the next flight at the flight readiness review, and there was another large piece of foam. This was the power ramp. And so they took the bipod ramps off after the Columbia accident. After our near miss, they took this large piece of foam off. They left these pieces of foam. And I tried to tell my boss, who was the center director, you know what, I don't think we should fly. He wouldn't listen to me. We went to the flight readiness review. Mike Coates, also a shuttle commander, Navy pilot, stands up and says, NASA's go for launch. NASA Johnson's Space Flight Center's go for launch. Charlie Camarda had to stand up and say, I'm Charlie Camarda, and I don't think we should fly. And so Mike Griffin, the NASA administrator, was there. I was fired from my job 3 days after this. I stood up and said we shouldn't fly. You think NASA changed this culture after the Columbia accident? You think we were psychologically safe? No. 2 other people stood up and said, you know what, I don't think we should fly. The head of safety and mission assurance and the chief engineer at NASA. And Mike Griffin, the NASA administrator, said, I'm going to accept the risk. This was the first time in the history of NASA that we flew a space shuttle with 2 items in the high risk, highly probable area of the risk matrix. In other words, the likelihood of it happening is probable, and the outcome would be catastrophic. We never flew a shuttle mission at a flight readiness review with that, and we flew, right? And then what happened? The 2 people that they didn't need my signature on the certificate of flight readiness, but the chief engineer and the head of safety and mission assurance, they basically struck out, I concur with proceeding with this mission. They didn't think we should fly, but they were not going to appeal what the administrator said. So we went ahead and flew with those ice frost ramps on there. So what do you think happened when we flew with those ice frost ramps? You think they came off? Yeah, they came off. And I was asked to be in mission control, even though they just fired me. They wanted me to be there to watch this video footage come down when we launched, and I did. And I went with my tail between my legs to the mission management team meeting, totally humiliated by being fired. And my boss came up to me and he said, "What do you think? You think it hit the wing leading edge?" I said, I couldn't tell from the video footage. So the crew was in orbit, and they had to wait the first day that they were in orbit when we opened up the payload bay doors like we did on my mission, and I had to fly the robotic arm to inspect the wings to make sure we didn't have any damage. When the crew did that and called up and said there was no damage, those same managers were jumping up and down, high-fiving each other like little kids, like, "Isn't this great?" Like, this is great, we're safe. Instead of, "Oh, by the grace of God, we almost lost another crew." This is the culture that is still at NASA right now. And I don't want to go into excruciating detail, but the 4th chapter in the book, I actually was fired. I was reassigned to this engineering and safety center, newly formed engineering and safety center. And because it looked to the public like, we really didn't fire Charlie Camarda. We have him in the safety center. We're going to listen to him. But really, they were canceling my voice. They put me there, and someone that was very powerful, Ralph Rowe, that was running it to make sure I didn't cause any more trouble. But I saw something wrong with my wing on my vehicle that we flew back, that we could have died. And it was in the silicon carbide coating of the wing leading edge. And I kept pushing, and I kept doing research, and I was prevented from getting the data, but I was able to get enough data to make the case that this is dangerous. We need to stop flying. There were 12 other panels on 3 of the vehicles that had a similar anomaly, but we could lose another flight. And I fought for about a year, and we launched 8 times. We could have had another failure until someone threatened me at NASA headquarters, and I guess they didn't know they were talking to a kid from Ozone Park, Queens, and I had to tell him exactly where to go, and it's the only time I use some bad language in the book. But I told my boss in headquarters that he didn't know who he was talking to, and if he didn't do something about this, I was going to the New York Times. And then all of a sudden, they started listening to me. Other people agreed that, this was a systemic problem. We have to change out these wing leading edges. And they did. But we could have lost another vehicle. And so if I would have written this book, it took me 18 years, right? If I wrote this book 18 years ago, I would have sounded like a whistleblower that was sour grapes, and I was angry and vengeful, but I didn't. I stayed at NASA because I love NASA, and I wanted to fix the problem. And like a researcher, I believe in the second half of the book, you'll see that some of my ideas for how do we fix problems like this in real organizations, I think they will work. I did a little bit of work proving with some of the teams how we do this, and I've worked with students, with some great people like Mike Ritchie and Jana Hitala. Mike Ritchie is the Chief Learning Officer at Boeing. Jana Hitala is this genius from Finland that I work with in my education program that we developed. And we presented the results to NASA, right? And we wanted to show NASA, hey, these are some ideas that we could change the organization. And no one would listen to us. And so I retired. And I decided to write this book. And I just want to show you that this is the team we put together. These were our ideas on how we do this. But more importantly, do you think NASA is a learning organization? All of a sudden, I'm writing the book and I'm watching Artemis fly around the moon, and I'm waiting to see the heat shield for Artemis, right? Because this is the most critical part, and that was the reason for them flying around the moon. This is the critical test. When I don't see the photographs of the heat shield, I'm saying something's wrong. Charlie Camarda's spidey sense is going off, and my radar is going up. I'm saying something doesn't look right. And I start slamming NASA on LinkedIn. And to the point where the administrator of NASA called me up at home and he said, "Don't worry, Charlie, we fixed the culture." And I told him where to go because the people he was listening to were the same people that were causing me problem and the reason for the cultural problem. And finally, the Inspector General basically showed this picture in a report, and then it was public. NASA was saying, well, we see something different in the heat shield than we were predicting. And then later on, as I kept slamming them on LinkedIn, it was, well, we had small pieces come off. No. Over 100 pieces, large pieces of the heat shield flake came off the vehicle. This is not something that is usual. This is worse than the Apollo heat shield, right? And that's why NASA hasn't flown another Artemis mission around the moon. I asked to help them. I asked to help form a team, the right team, to help solve this problem. Crickets again. If you don't see Artemis fly, if God forbid something happens to the next crew that flies around, and actually put a crew on that vehicle when they fly around the moon, you are going to see Charlie Camarda going crazy. But what I'm telling you is, it's very hard to change culture. Whether or not Boeing could do it, I don't know. They weren't successful after the 737 MAX issues. They went through several CEOs, right? We got a new CEO at Boeing. Right now they had the Starliner problem in the space division. It's very difficult to change the culture. And the second half of the book talks about what it takes to change that culture. Some ideas are doing that. It's not complete, because if I had another life to live, my passion would be to work with these great sociologists, psychologists, people in artificial intelligence, to develop the techniques to model the behaviors on teams of people solving these kinds of problems, so we can identify when you have a problem in a small team, when they don't have the right information, when they're making a bad decision. And it's my hope that this gets the discussion going so that we can actually solve these problems, because they're very difficult. And I hope I didn't bore you to tears. And I hope when you read the book, if you're so inclined and you think it's worthwhile and you have the right technical background and would like to collaborate or would like to convince your university to do research in this area, because I think, for instance, NYU would be perfect, because you have the engineering expertise, you also have the humanities, the sociologists, the psychologists, behavioral science, you also have the computer scientists, and that's what it'll take. And I think I could put together a program and get high school and university students working together. That's why I called my program the Epic Education Program, the Epic Challenge Program, to work on really cool problems like this. Teach them how to be engineers using challenge-based learning, but yes, also use them as guinea pigs so we can conduct research on what we're doing. So we need an IRB to do that. We need a university to do that. And I'm going to open it up for questions right now, because I didn't want to bore you to tears. And so if anyone has any thoughts, any questions, please.
Questions? We'll bring the mic around to you and then take it back to Charlie. We have a question? Ready? Here you go.
Hi, thanks so much for an interesting talk. I'm wondering if you have any opinion on the ISS. We're hearing that the Russian side has leaks, and the press is saying that this could be catastrophic failure.
That's interesting.
Charlie, have thoughts?
That's interesting. My good friend here, Burke Allen, set me up with a couple of news interviews, one on WPIX that you could Google and get, and one at WABC News channel that I just did yesterday. And they asked me the exact same question. this is a critical problem. They have a leak on the Russian side of the International Space Station, and it's very serious. But you're just starting to hear about it now. But the astronauts have been living with this risky situation. There's either a crack or there's a leak somewhere in the docking compartment on the Zvezda, the Russian side of the vehicle, the command module on the vehicle. And so they have to keep this hatch closed because they don't know if that leak is growing. It's not a critically bad leak, but since we don't know what's causing it, if it's little micro cracks, those cracks could propagate very quickly. They can merge. Remember, some of you old enough to remember Aloha Airlines when the top of the 747 came off? It could happen
737.
37? No, 47.
No, Aloha, where the top.
Aloha?
Yeah,
Hawaiian
absolutely
Airlines.
sure. It's a 737.
Okay.
Yeah.
Okay. 737. Okay. It can happen that quickly, rapid decompression. And so when they open that hatch, I'm so glad we have knowledgeable people here that can straighten me out. They have to be close to their rescue vehicles, either the Soyuz vehicle or the Crew Dragon that's up there, because they might have to jump in there and come home. That's really dangerous. What's the problem? The Russians don't give us the data. They won't tell us. The U.S. doesn't push on the Russians to tell us what's happening over there. It's a very delicate dance they have to do, and it really upsets the hell out of me, and it worries me because we almost lost 2 American crews on the Soyuz coming back that were in my class, Don Pettit and Peggy Whitson, and the Russians don't tell us what's happening. And so, yeah, that's a very critical problem. The space station's getting older, and you know what? NASA didn't think it was an experimental vehicle. They never instrumented it. So how the heck are we going to predict when cracks happen if we don't understand the loading conditions that the entire space station is seeing?
All right. Anybody else? Got a question right here, sir? I'll get back to you.
Yeah, don't go to that guy. He's a troublemaker. I'm only kidding.
Thank you for your presentation and your service to the country. I had read that the foam problem was related to the removal of CFCs in the application process. Is that not?
That wasn't this one. No, you're absolutely right. There was a major problem with the external foam on the external tank. The cryogenic tank is a closed cell foam called SOFI, spray-on foam insulation. It has several different types of foam, and at one time, because of environmental protection, they had to change the CFCs, the blowing agent, in those small little foam particles. And when they did that, you are absolutely right. Large areas, but not large pieces, but a lot of foam popped off, almost like popcorn. And the belly of the shuttle orbiter and the shuttle tiles, 30,000 shuttle tiles, it looked like it got sprayed with a shotgun. It was like over 300 areas where you had damage to the shuttle foam that was over an inch. And so that's what I'm talking about for highly coupled systems and for interdisciplinary systems. A very small change could cause a catastrophic event to happen. But that wasn't the reason for this. I have a couple of technical papers. One of them kind of talks about what we think is the most likely cause of the bipod coming off. But the foam coming off in all the other different regions, totally different, could have been totally different failure mechanisms. That's why we could never predict that was going to happen or when it was going to happen. And so this was an inherently dangerous vehicle. A 1 in 67 chance that you aren't coming back on this vehicle. Probably the most dangerous space vehicle, even more so than the Russian Soyuz vehicle.
Getting back to the gentleman back here.
Hi, I was just wondering if you have any insight on why the engineers of the shuttle didn't reinforce brittle materials in an area that's so, sorry, give me a second, failure critical as a leading edge with something that had a more, a material that had more tensile strength, backing of either fiberglass or maybe titanium sheeting, something like that. I'm just throwing ideas out there.
Yeah, this is something I know a little bit about.
That's a great question. And as a layman, I've always wondered, it's like, You got styrofoam underneath the shuttle, right? You know, so what's the story here?
Yeah, no, you're absolutely right. You have to understand these were like epic challenges to solve. I mean, what material could withstand 3,000 degrees Fahrenheit for over 15 minutes? And what would the strength of that material be, right? So carbon was a new material, and the silicon carbide coating spent lots of years. First, it was developed for missile nose cones, right? And so this was the only material that could take it. My first job as a NASA engineer was testing what was called a heat pipe cooled leading edge. You know what that is? It's using heat pipes to basically cool the stagnation region of the wing leading edge.
Heat pipes are amazing.
What's that?
Heat pipes are amazing.
Okay. So we could talk about it for a long time, but by doing that, you can actually develop a metallic wing leading edge. But NASA didn't invest in that research anymore, right? So we could have had a more durable wing leading edge, and I have one sitting in my study that was made out of a superalloy material to withstand it. So these are very difficult problems to solve. You know, SpaceX is having problems with thermal protection systems. These challenges don't go away. But by not putting money in applied research, we are not looking into the future. NASA is not developing the next generation, the next propulsion system, the more advanced materials. We have very limited research dollars going into that funding because we're wasting a lot of money putting humans on a space station and trying to go back to the moon with humans. And we need to totally transform NASA, DOGE. I hope, Vivek, I know Elon can't do it because it will be conflict of interest, but maybe Vivek will help figure out how to do this. And I talk a little bit about how we could do this in the book.
All right. We got time for 2 more questions. Let me go back this way. Do you, sir?
Sure.
All right.
Commander, isn't one of your patents dealing with heat pump? And the other question I have is, did you ever think of going over to SpaceX and trying to help them?
The patent on the heat pump and SpaceX.
Yeah, I have a few patents on heat pipes. And, you know, I've thought about it, but I would like to do it just as a consultant to Elon. But if anybody knows anything about Elon and how SpaceX operates, and you might get a little bit from it, talking about the people they want to hire for DOGE, they don't want these idea people. They want young people that want to work 80 hours and totally get burned out. And I think I could do it, you know, but I don't have the technical chops because I haven't been doing that in a long time. But what I do have is the experience to help train young people in how to do this the right way. And I don't think Elon wants that. And I'm not sure that Elon understands what a research culture is. I know they're doing a lot of things the right way. They're failing smart, fast, small, cheap, early and often. They just launched another Starship. I wasn't able because we're here to see exactly how they did. They look like they're learning from failure, but the way I taught and teach engineers to do this as researchers, failing smart, fast, small, cheap, early and often, what you saw with the team that did the foam stuff, we rapidly test lots of material very quickly, small pieces, understanding the physics of the problem, and then we can construct these large modules using a building block approach to solve these problems. I don't know if that's what Elon does, but he seems to be doing things a lot better than NASA. Okay, and that's unfortunate. I was at a panel session in Berkeley, California in 2012 when I was still at NYU Poly on detail, and a young person in the audience goes, you know, why is, and this is when Elon was just being successful with the Falcon 9, he says, how come NASA isn't like SpaceX? And I looked at him, I said, you young punk, NASA was SpaceX 50 years ago.
All right, one more question. Yes, sir.
Charlie, once again, thank you for your great program here. It's fantastic. You basically answered half of the question. What's your personal feeling between NASA and their thinking and their culture and SpaceX with Elon Musk?
Yeah, and that's, you know, they thank you for the question. What do I think of culture at NASA and the culture at SpaceX. And I really can't talk about the culture at SpaceX because I don't know. I'm looking at it as an outsider. I'm watching what they're doing. I'm watching them fail. I'm watching them learn. I know he's burning out the people, and that's not a good thing. I mean, for you to have a good research culture, you have to allow people to fail, and he's doing that, and allow people to learn, but you have to give them time, and you have to mentor them. If you keep turning around the people, turnover in your organization, that worries me a little bit, you know? And I would like to talk to him about that. I would love to see us transform NASA so that we go back to the NACA days when NASA is a research organization looking at the far-term technology, doing that advanced research, building up that expertise to help our folks in industry come up with new propulsion systems, new materials, new ways of developing thermal protection systems to solve some of their challenges. The way we did it back then, it was a much smaller, much leaner organization, and it was a lot more efficient.
Before we wrap up, how many of your parents or grandparents, would you raise your hands? So Charlie, I want to ask you, this is the launch day for the book, and you've answered a lot of technical questions, but I want to ask you a personal question. You took NASA to task after Columbia. You told them what was going to happen. You said, I don't want to fly, and they got you to fly.
No, I didn't want them to fly. Other people. I got on the vehicle.
You did get on the vehicle, and you're a single dad, a single father, and you get up there, and it almost all goes bad, really bad. And your little girl wouldn't have had a daddy anymore. What went through your mind when you got the news up there that things were going really bad? And were you scared? What did you think about what would happen to Chelsea? Talk to us about your thoughts as a father when all that happened.
You know, it's strange. No one ever really asked me that question. And you know, my daughter was a teenager, and I always wanted to know, and she always acted like, this is no big deal. Like most teenagers, you know, your father's going to fly in space. But when you're out there on a launch pad, how many people have watched a shuttle flight or a launch, right? And you're like 3 to 6 miles away, right? And you can't, all of a sudden you see the engines light off. You don't hear a thing, right? Because good old light's traveling faster. Then all of a sudden you feel the engines kick in. And all of a sudden you feel the pressure waves pounding against your chest. And you feel that. I wanted my good friend, Rick Lenahan, astronaut, in charge of taking care of my family. When I'm doing this, in case something bad goes wrong, I said, Rick, take a picture of Chelsea because I want to see the expression on her face. I know she's this arrogant little teenager that thinks, I wanted to see fear in her face, and he forgot to do it. But to get back to your question, Burke, you know, we always write that letter in case we don't come back. You know, wish I had it. I don't know what my friend Rick Lenahan did with it, but I was a crew escort, a family escort at one time. And that's a tough time, you know, because I watched my friends not come home. They didn't come back to the launch pad. And, you know, this was the first time we were flying, and this was the first time that a vehicle, we lost the crew during entry. And so the family was waiting at the Cape, and they never got there. And so I wasn't worried so much for myself, but I was thinking that the families, it was much tougher on the families waiting to see whether or not we were going to make it through that 15 minutes or not. And so I didn't have any fear when I launched. I didn't have any fear when I re-entered the atmosphere, entered the Earth's atmosphere. Not because I'm a brave person, but because I knew everything that could possibly go wrong. I knew the team on the ground, the friends of Charlie that I had. When I flew in space, we had no trust in the people on the ground. In my crew notebook, I had all those experts that I knew for those 22 years in my crew network, in my crew notebook. I could call them up on their cell phone without going through mission control. And I could talk to them directly, and we did, in order to make the right decision, pull the gap filler, that almost cost us our life if we didn't do that. If they made the wrong decision on the ground, we went to the Friends of Charlie on the ground and said, you got to do this emergency spacewalk or you guys aren't coming home. That was a little bit of a tough time, but I knew we could do it. And so you train on these missions, and I like to think of it almost like a Navy SEAL team, but not quite. And we cross-trained and we trained for a year and a half. And with the people on the ground and the people that I knew and the people that I worked with and my crew, I felt pretty confident that we were gonna fix this and we were gonna be okay. The good thing that we had that the other crew didn't have, we could inspect the vehicle before we came home. We knew everything was okay, and unless something else went wrong.
Ladies and gentlemen, Charlie and Camarda.
I want to thank you all for coming. Our curator, Josh Stoff, has told me that if you want to see a leading edge, we actually have one over here in the Space Gallery.
That's right. That's right.
So, the model over there in the Space Gallery, but we appreciate you coming out tonight. How about one big round of applause for Charlie? And he will meet you out front if you have the book and you want him to sign it. So thanks again.